proposal that we have drafted is in microgrid system and how in microfinancing system is very applied project because the client called target companies applied research on microgrid system and how to bring it into the market. And our contribution in this project, we will have the possibility to place, I think, 12 students. And the ideas will be that they work on master thesis, which will be also business cases, because the project itself is really applied oriented. We don't have a formal frame so far now, but we will have to design innovative solution to bring team.
Thank you. Thank you. Maybe only very last question, and then we move on. Yes.
Thank you very much for the presentation. My name is Florian Weiss from the Berlin University of Technology, and my question is related to the hundreds of households not with energy supply in, for instance, sub-Saharan Africa. How or does PAUWES research on cluster methods to find and to identify the unelectrified households in order to choose adequate instruments, so extending of the main grid, microgrids, swarm grids, whatever, solar home systems, so to cluster the unelectrified households, for instance.
I think I'll take the questions. I think this rural electrification is one of the main topic among the students in terms of master thesis. PAUWES itself is not a project implementing agency, so it doesn't do anything towards providing the electricity. What it is doing is basically providing students who can take care of those questions in their research in form of master thesis right now. Okay. It is serious issue, yes. Serious issue, but without a concrete solution. Nowhere, not only in sub-Saharan Africa, also elsewhere.
Thank you.
Very last, then
Okay. Thank you very much for the opportunity. In our presentations, in the last 2 slides, the request was to give ideas on areas of collaboration, and the next one was on what innovations that exist that could be taken to practice, yeah? So my question is that what mechanisms exist or are planned for in terms of establishing these collaborations?
For the very interesting question. Also the aim of this meeting. So for now we have the position of research coordinator that I'm holding, which is more or less the focal point of, let's say, organizing all cooperation initiative and activities. The only answer that I will say is welcome, highly appreciated to see that is an interest. Just let's follow up later on to see what we can do. And I've started already with short-term lecturers, as I was mentioning in the previous slide. When there are PAUWES for 2 weeks, we draft together 1-pagers, and based on the research priority of PAUWES and the interest of the researchers, and he go back in his home countries. When he see an interesting grant, then he contact us. What we could do at PAUWES is to mobilize partners. You know, you have a strong mandate also with the African Union. If there's an interesting project where you, for example, have a case study that you have to upscale in other countries, and when you need an institution who will be warranted to facilitate this process, we have a direct link to the Commission where we could have a kind of recommendation letter, and that are the things that are very welcome for the donors at the BMBF. When they see that in the project application, you have a kind of letter of support of high-level official. I think this facilitation at this level, that is something that we could bring into a cooperation, but also partners. We have now with our short-term lecturers a database of almost 120 lecturers, meaning that we could also see other institutions which could fit to the project proposal, to the 1-pager that we have drafted, that we could bring in. And then, as I say, we could mobilize, we could organize. That is more or less the framework that we can offer so far, and together we go for fundings. I think in the nutshell, that is how it's worked. And for more details, you just have to send me a mail, and then we will see how to proceed.
Okay, thank you very much, Eric, and for all of you those who asked the questions, and to all of you who listened very well. And if there are further questions regarding research agenda at PAUWES in energy, then we can also have informal discussions. As I said, I can offer also my time afterwards. Now, I would like to move with the next presenter, that is Mr. Mohammad Mera, and he's going to talk about a very nice thing about photovoltaics.
Take the pictures and make
Relax. Relax.
Hello, I'm Mohamed Mirah from the University of Tlemcen, PhD researcher. I would like today to present my following topic, giving some research outcomes about simulation and comparison between conventional and engineered back boost converter for grid-connected PV systems. So this work is supervised by Professor Res2Prac and Professor Abdelmajid Boumediene from the University of Tlemcen and Laboratoire d'Automatique. For the next slide, I will give the introduction, some short introduction, and then I'll move to the conventional back boost converter. After that, I move to interleaved back boost converter, and after the comparison and the results and the discussions, and I finish with the conclusion.
Shall I bring the slides either? Just
so the first reason is the affectation of the economy of Algeria in changes of oil prices from 108 USD to 35 USD per in oil prices per barrel. The second reason is that the cost of electrical energy is the cheapest one. It's about 0.04 USD per kilowatt hour in Algeria, which is due to the biggest share of the cost being covered by subsidies. So these later factors pushed the Algerian government to take or to invest in renewable energy. So the government of Algeria decided to present a plan of work and a project to support renewable energy. Algeria has drawn a roadmap to reach an installed capacity of 22 gigawatts in 2030. The most part is taken by the photovoltaic energy, about 13 gigawatts, because of the potential of irradiation in Algeria. So the first of all, I will talk about the DC-DC stage, which is the converter we used in our experimental. So the proposed DC-DC converter is a part of a grid-connected PV system. It's containing a photovoltaic panel, then a DC-DC stage, which is an interleaved back boost converter, then an inverter. After that, I use a filter and a transformer to transform this the energy generated from the PV panel to the grid. So the vast domain of DC-DC converters has experienced a variety of research. In my study, I used the interleaved one in order to give more efficiency to my system. For the conventional back boost converter circuits, the first figure presents the circuits containing the switch, the inductor, and the capacitor. We noticed that the input voltage or the output voltage in inverted comparing to the input voltage, and the gain obtained can be more less or more than 1. In mathematical modeling of the system, I found the differential equations which define this circuit. Then the interleaved one is that means I put 2 parallel back boost converter to gain some benefits, and the components are designed as below: the resistors, the input and the output capacitor, and the inductor. Here I give some specification about the photovoltaic panel and the other components. We used a PV panel of 29 volt and frequency or switching frequency of 60 kilohertz and a duty cycle of 0.52. And the components are designed like capacitor, inductors, where we used 2 inductors and 2 capacitors, the input and the input and the output one.
She's taking picture.
Here in these figures, the first one, it shows the current waveforms, and with the switching or the PWM waveforms of the control. And the second figures is a comparison between the input current of a conventional and interleaved back boost converter. We can see the big difference between the first and the second one in the input current. After that, the first figure we will talk about the output voltage. If we see or we compare the waveforms, we see in the second one, the waveforms of the voltage are less than the first one. It means the interleaved back boost converter has shown a big efficiency. And moving to the second figure, we can show it shows that the output current also is reduced, comparing from the output current of the back boost converter and the interleaved one. For conclusion, both input and output voltage, current and voltage ripples were reduced, and efficiency was improved. The size of the inductors, so the second benefit is that the size of the inductors is reduced because we used 2 inductors in parallel. So the interleaved back boost converter presents less switching power losses and has a higher efficiency in respect to the conventional back boost converter. So while having an interleaved structure can cost additional inductor and power switching device. This is the only inconvenience. So I will finish with the cooperation between my thesis and the other students. Like for example, the purpose is to build an experimental board used by PAUWES PhD students and master and PAUWES master students. After that, while looking for partners to build a prototype of my experience, and why not building a startup, then selling the product, also build and sell for Africa and sell for the European community. Thank you for so feel free to ask any questions. Yes? Yes?
So thank you very much for your presentation. It was very nice. I would suggest that we collect the questions and make it afterwards in the podium. Thank you very much. And now I would like to request Dr. Mercy Manusi, and she is proposing a solution how to avoid charcoal, because we had this word yesterday.
Good morning once again. I cannot find my presentation.
I'll try.
Good morning, colleagues. I'm going to present my work on the potential to produce biogas from tannery waste. Well, he said I'm going to talk about charcoal. It's my separate work that I'm doing altogether. Okay, why are we motivated to do this study? In Zimbabwe, we've got several tannery industries, and there's huge accumulation of tannery waste. And I'm sure this is also a condition that is common in most African countries. There's then a resultant of environmental pollution. The tannery waste is just there, and then there's need for its proper management. So the proposal is to harness biogas from it, because Africa as a country, we also have an energy deficit, and biogas can also be one of the solutions to reduce that problem. There's also the energy food nexus that have been talked about even by the previous presenters. When we digest the biogas, one of the resultant products is the digestate that can be fed as biofertilizers. And also there's the climate change effects. This morning I was talking to one of the participants that currently in my country, back then when I was growing up, we knew we were supposed to be going into winter, but now we are still receiving the rains, which is why we need to take corrective action as researchers. If any material is biodegradable and we let it rot, then we are emitting the methane and carbon dioxide into the environment, which effectively results in climate change. So this research is also looking into mitigating that process. From the tannery processing industry, a lot of bio-waste is generated with collagen and other fish taking the major composition. And then these are then the raw materials for biogas production. So in our study, we proposed a closed system, because also the world is looking at circular economy. If you have a raw material, we need to harness it in such a way that it feeds back into the system. So in this work, we're saying that if we have our waste and after biogas digestion, it's either we send this biogas for electricity generation, and then it is fed back into the system so that the equipment that require electrical energy or any other heating energy can utilize that biogas. So from the lab work, we realized that the biological oxygen demand and the chemical oxygen demand significantly reduced when we did the work over 45 days. And in literature, it is reported that when our coefficient for biodegradability is greater than 0.5, it actually shows that the material is highly biodegradable, such that ternary waste is one of such material. And the biogas can be produced well under mesophilic conditions of 35 degrees Celsius. And the range of the biogas was between 55 to 65%. The digestate, as I indicated earlier, can actually be a solution to produce biofertilizers. So, as a way forward in terms of interactions and collaboration with PAUWES, I thought there's need for collaboration in valorization of biomass, not just the ternary waste, but any other biomass which is common in Africa, mostly is the sub-Saharan Africa, being it an agro-based area. There's a lot of biomass that we can use, and we can use this biomass for biogas. If the students were working in this area for the briquettes yesterday, there was a heated argument where people were still thinking that we are making charcoal from trees. But the trend these days is people are making the charcoal briquettes from waste biomass. So this is also another area of collaboration and interaction on how best we can have clean energy. There's also the biofuels that we can take on together. In sub-Saharan Africa, there's a lot of sawdust, there's a lot of bagasse, and we can algae in the wastewater, in the water treatment industry. And from this area, we can also take the biofuels as part of research and probably link it to practice. There's also need to collaborate. Probably that's when now the tech hubs and the startup companies can come into place, when we can look at scaling up of these ideas. All this waste that I've been talking about, the biomass is being generated by companies. So if there's now that linkage between the research and the tech hubs, then we can have startup companies that can take this product to the market. There's also potential for co-supervision and hosting of the master's students. So yeah, in terms of transformation to practice, I've talked about that. Initially, when people hadn't realized that waste is actually money, it was a nuisance. But right now, when I see waste, I think, what can I make from that type of waste? Thank you.
So thank you very much again, and Mike. And we don't stop attacking our charcoal. So we have next presentation also to attack charcoal for cooking. PAUWES. They are all video.
Put them all in the website or
Page, but if he needs to copy the paste.
Any IT expert in the room?
Okay, thank you everyone. My name is Bernard Tabo from Uganda. I've just graduated with Master of Science in Physics, where I specialize in solar energy from Makerere University. Currently, I'm teaching at Wood University as an assistant lecturer. Wood University is about 340 kilometers north of Kampala, for those who have been in Kampala. My research areas for masters was on thermal energy storage system for solar domestic cooking application, but specifically I was looking at the thermal performance, experimental evaluation of thermal performance of some few selected oils for indirect solar cooking applications. Now, when you take a case of developing countries, I don't know here, but mostly you find that for cooking, the majority of the population actually depends on wood fuel. The situation in Uganda is equally not different. About 94% of the population actually depend on wood fuel for cooking. And when you look at wood fuel and charcoal are actually not sustainable. And when you over depend, that means you're going to destroy this forest. And when you destroy forest, that would result into problem with low agricultural production, which results into famine and issues related with climate change. And yet, for the case of Uganda, we are really blessed. We have amount of sunshine is about 5 to 6, as per that citation, 5 to 6 kilowatts square meter per day for 8 hours. And that can be really a good source for us. And you know that sun still it has some lifetime of about 12 billion years. So the energy is actually sustainable. Now, we can use sun as someone was talking of photovoltaics, and also we use it as heat directly. And my focus was on my focus is to see how we can utilize sun as heat. Now, we have solar cookers, even probably here and also where in parts of the world people are using solar cookers. But these solar cookers have limitations in the sense that during a time when there is no sunshine, you cannot use. So it is really, that's why my research was looking at how can we really store this sun energy in form of heat, such that you are able to cook at any time of the day. And I was looking at the cheapest mean of storage, which is a sensible heat storage system, and that requires materials like rocks, oils, water, hair, and so forth. I zero on oil basing on the fact that oil has a high density, and also it has a high smoke point, and also it can act as a heat transfer fluid and also heat storage medium. Now I've selected 3 oils basing on their appropriate thermophysical properties. I've selected refined sunflower oil. I've also selected refined palm oil, and also I selected thamia bee. The 2 refined palm oil and refined sunflower oil, those are vegetable oils, but thamia bee is an industrial oil, especially used by in industries for cooling purposes. Now, in Uganda, the performance, how this oil really perform in case when you subject to it, actually there are really very limited literature on the performance of those 3 oils. And that's why I looked at the thermal performance of the 3 oils to see which one is better in case we use it for thermal energy storage system. Now, I used thermosiphon principle because thermosiphon principle is a self-circulation of liquid. So I used thermosiphon principle for charging my oil because it is very cheap, and it's in the sense that it does not require a pump. And this that was my experimental setup. This was the fabrication, and this is what I've fabricated. This is the boiler, and this is the storage tank, because I was interested in looking at the energy stored and the exergy, which is the quality of the energy available. I was also looking at the thermal stratification, which is the energy distribution along the storage tank. Now the design actually the design is like this. This is a copper pipe, which passed through this boiler, and it's a continuous pipe. So this is my boiler. This is where I put oil, and in this oil, the oil is heated by an electrical heater, and this heat is indirectly heating the oil, which is stored in this boiler. This is my storage tank. So after heating this, the oil comes, gets heated. The cold oil comes from down here, gets heated, and then it goes up because of the density difference. The hot oil are actually lighter, and the cold one are heavier. So that results into the saturation of the oil, and hence the energy stored here, which preliminarily the indication are actually the temperature. Now, this was my experimental setup. In here I had 10 liters of this oil, or one at a time. For a case, probably if it is a refined sunflower, I put 10 liters here, and here was 4 liters. And then I was interested in the temperature distribution along this tank, which will enable me to determine all the parameters of interest. So I inserted thermocouples at a distance of 5 centimeters each, and all these thermocouples, there were 7 thermocouples, because the size of my storage tank was 40 centimeters, and these thermocouples were connected to a data logger, a TC data logger, and the TC data logger was configured to measure the temperature at every 1 minute, and interface with a computer to retrieve the data, and also this is the boiler, which is connected to a heater. So the heater, this boiler was heated for 6 hours, and then the oil were saturated, and the temperature were measured at different times, and I was able to analyze the performance using some equations, and also MATLAB for analysis. These were the temperature distribution profile of the boiler. It is of interest because you realize that I never had an automatic temperature controller. So I was controlling the temperature of the boiler manually. And this was the temperature profile of the boiler for charging the refined sunflower. This one was the temperature profile of the boiler for charging the refined palm oil, and this one was for Thamia B. But when you see, it is almost, the temperature was maintained between 230 to 220 to 230 degrees. But of course, with some pikes, the pikes was due to manual control of the boiler, and hence it is not very perfect. But even when you use temperature controller, the limits, the variation, the fluctuation is within the appreciable limits. These were the temperature profiles of the storage tank for refined palm oil, for the refined sunflower. This is for the refined palm oil, and this is also for Thamia B. Now the blue one is the temperature at the top of the storage tank, and then this 5 centimeters from the top of the storage tank. But of course, taken time, the charging was 6 hours. And this one was second, 5 centimeters. And there's a huge gap here because the third thermocouple has some problem, and hence I was not in position to retrieve the data for the third thermocouples. The same thing with these for refined palm oil and also for Thamia B. Now, the temperature profiles are actually comparable, but when you take a case of for the first 1 hour, then you realize that there's actually a huge difference, and that was the point of interest. You realize that for refined palm oil was really so high compared to refined sunflower was higher than refined palm oil, which is again higher than this. This is basically attributed to high density of refined sunflower, which absorbs large amount of heat at the initial point of the charging. Now, I was also interested in the thermal gradient, which is the energy distribution per centimeters along the tank. You realize that within the first 1 hour it is comparable. For refined palm oil and refined sunflower, they were comparable, but for Thamia B is very low. Thamia B has a very low density. The density is about 890, while for refined palm oil is about 960, and this is 970, and you realize that that's why it's comparable. But in the slides, when you look at towards the end of the charging, there's a bit of declination. Basically, is because of the variation of the thermophysical properties. Because when you heat the coil, the density reduces, but the thermal conductivity increases. So the thermal conductivity for refined palm oil actually increases faster than the density, and hence there's a slight decrease towards the end of the charging. And this was my temperature distribution along the storage tank. You realize that at the start, this is a time, at the initial start, it's a straight line, meaning that the temperature from the top of the tank is actually comparatively the same. But at the first 1 hour, there's a big inclination, realizing that this is the temperature at the top, and there's a very huge difference between the temperature at the top compared to the temperature at the bottom, and that shows that there's a high thermal stratification, which is one parameter which also determines the quality of energy. Then for this is very low, but when you compare this refined sunflower and refined palm oil, then you realize that this was higher, though it's a bit comparable, but it was higher, slightly higher than for refined palm oil. Okay, fine. Then this is the thermal stratification, which is the number. It's a function of the gradient, initial gradient to ratio of gradient at a given time to initial gradient. But still within the first 1 hour, it's for refined palm oil and Thamia B. Refined palm oil and refined sunflower were comparable, but Thamia B was very low. These are the energy. This is the energy distribution. Still within the first 1 hour was comparable. But this is the exergy. Exergy indicates the quality of the energy. So if you store the energy, how much will you retrieve? So I was also trying to look at, and you realize that refined palm oil and refined sunflower, within the first 1 hour, they have a comparable energy, which was higher than Thamia B. Now, in my conclusion, yes, we can use both refined sunflower and palm oil, but of course, refined sunflower is more preferred because of the high initial stratification and energy, and hence it can be used to store energy. It can be used to absorb large amount of solar energy, and the duration of solar energy is also short, so we need that. Then also, basically, because of the stored energy was also high, but I wanted also to look at the issue of optimization, especially isolating the materials, then looking at the recycling, how many times should you recycle this oil? Then cooperation with the PAUWES, I was looking at training because this was my master's, so probably I need to go for PhD and then to further this and also create a kind of a prototype and a field, carrying out a field visit in case PAUWES has some project like this. I would also wish to see what they are really doing. And in research for practice, I want now to have the solar cookers incorporated with TESS, because that was thermal energy storage system. But now I want to get a prototype and then implement it and probably take it to public places like schools, because I've seen in India something, they are using concentrators for cooking schools, but they don't have thermal energy storage system. These were acknowledgement, PAUWES, and all those who helped me in my research. Thank you for listening.
Vietnamese for charcoal, and now we have the next presenter, Martin Lambai, and he will tell us how to purchase those things.
Thank you very much, everyone. Although my approach for the research is a bit different, but I will welcome everyone to this presentation. Okay, I'm looking at public-private partnership investments. I'm sure it's somewhat new concept in some countries here in Africa, but it has worked in other sectors. It has worked in other sectors, like in the infrastructure sector. I'm from Zambia, and those are my phonemes, and I run my own small freelance consultants who deal with energy services. So from what I've been doing, I realized like there has been a problem, especially in deploying renewable energy, and people come, they want to invest, and they have been facing this challenge. So that's how I thought of using a different approach, seeing what other models, business models have been used in other sectors, and see if we can apply them in the energy sector. Okay, so briefly, just an introduction. We can see that from the year, for a period of about 14 years, in Zambia, access to electricity, there has just been an increment of about 11%. So we see 14 years period, and 11% has been achieved. And we could still see that there is a very, very big there's room for development, especially for rural areas. In fact, like within that 14 years, only about 1% has been done, and we see that in Zambia about over 68% of the people still live in rural areas, and the population keeps on increasing annually. By 2003, the population was about 13 million. It was about 9 million, but as for now, it has gone to about 16 million. And you see the people living who have access to electricity as of now, currently it's still around 27%. The 27% is for the year 2017, not 2014. Now, looking at background, what has been done so far. So I gathered some pieces of information from rural electrification agency in Zambia. It was created in 2003. It's a one that manages all these projects it's called a special purpose vehicle. It's funded by, it depends on donor funds and also government budget. So that's why most of the money for electricity, for electrification comes from. So they have a vision, they say from 2008 to 2030, and it's also under the Vision 2030 for Zambia. So they are planning to increase access to electricity for people living in rural areas from 3% to about that's about 51%. And in their report, they indicated like they have a total budget of about $1.1 billion US, and don't know where it's going to come from for them to achieve that target. But what they have been doing currently is just been on grid extension. They spent, from the time when the agency was formed, they spent about 600 million on grid extension, which covered about 3,500 kilometers. That's what has been extended. But it has just been on they are fully focused on connecting new districts Zambia. And on they have a component for renewable energy, of which it has only benefited about 118,000 people just through solar projects. Now you can see that they clearly stated that for them to operate efficiently, they need like a budget of $50 million yearly for them to operate efficiently. But this, if you look at it, this is only on the public sector side. This is a public institution. Now, since it's a public institution, it depends on money from the government and also from donor funds and also loans. So, considering also the cost of electricity, which is extremely low, these projects, they don't really look sustainable if the government was to spend that money and they get yes. Okay. So, coming back again, the bigger challenge has still been on the electricity system in Zambia. It's still vertical. Simply can say it's still it's entirely owned by the government. We say like this is a ministry. Then we have the regulatory authority and the special purpose vehicle, which is Rural Electrification Authority. This is the utility company. We could say like the utility company owns everything from generation, transmission, distribution. We could say like 94% and the transmission is 69%, and the remaining percentages are being run by these other private sector. These have been there for quite a long time. So now we can still relate why there hasn't been improvement in accelerating energy access. It's because of the market system. There hasn't been much of private sector improvement. And coming back, like most of the electricity that is generated, it goes to the mining companies. Those are the major consumers. And there have been some projections that for the year 2018, the mining companies are going to consume more than 49%. For residential areas, 15% projected increase. But considering that the country, on the other side, it entirely depends on hydropower for generating electricity, and we still have a deficit of about 200 megawatts, and the consumption is increasing by 100 megawatts every day. So we see like the demand is higher than the current generation. So what I'm proposing here, it's something I found out. It's really working out in the road sector. Currently, the roads were bad as well, but they use this model, which is called public-private partnership. There are different models under this. So far, like somebody put up a road and get back the money within a period of time through progress. But if it has worked in the road sector, and we can see like the roads have been improved and it's really working out, we can also apply the same concept in the energy sector. So this whole concept started under Zambia Development Agency. It was introduced there. They have a PPP framework. It was introduced in 2008. So simply here they're trying to, the private sector invest in the energy sector. They use their money to invest in the energy sector, and under a concession period, maybe 20 years, they get back their money and they hand it over to the government. That's under a different model. So you see, here we have the private sector and the government. They are due on a concession, maybe let's say 25 years. So the private sector is going to use all its money to invest in the energy sector, and then it feels like we're going to accelerate energy access. If we could have such, instead of having the government on the middle, doing everything. If the government doesn't have money, or doing the national budget, you find like they cannot give all the money to the energy sector. It's not really sustainable for them. Then currently, this is what has been done by rural electrification agents. This is what I found out when I put up all the pieces together. Bridge extension so far, they only spent about 600 million, that is about 3,500 kilometers that has been done. This is the output, not really the number of people. You see the number of projects that has been done under the 600 million. They have only done 161 bridge extension projects. Then, when it comes to solar, they have spent about $2.6 million, and these are the number of solar home systems that they have deployed so far, about 1,000. Then, when it comes to mini hydro, only one mini hydro station plant was installed in some area, and we spent about 8.7 million, and it is benefiting about 12,000 people in the country. When it comes to wind is totally, they are still doing some feasibility studies. Okay. So I gathered information on different PPP models. There are about 5. The first one is, so there's need for, we're trying to see how this can really help in Zambia. It's called the build, own, operate, transfer model. So in this case, you find a private investor is going to use his finance to build up a power plant. He's going to own it for a period of time. He's going to own it for a period of time and operate it. Then, let's say after 25 years, he's going to transfer it to the government. So in that case, he's guaranteed that he might have gotten back his money, and during the transfer time, the government is going to pay that private investor. They call it a balance, just to balance of what he spent on that. So it's really good. It's really good. It's a really good model. It's applicable simply for bigger projects. Say for bigger projects, let's say for hydro power plants. Instead of the country going to borrow money to put up that hydro power plant, an investor can put up that hydro power plant, and maybe after 50 years, that hydro power plant will be given back to the government. So within this model, we are guaranteed that access to electricity will be accelerated. Okay? But further, there is need to come up with to assess different financing models instead of equity and dividend and loans from the bank. Grants can also come in to offset the initial cost. Then we also have another one, it's called the build, own, operate. But in this case, an investor will just build the power plant and own it and operate it. There's nothing like handing it over to the government. So this is the case of what has been agreed right now with it's a Russian company. Zambia wants to go nuclear. I got this, it was from Turkey, but it's the same model they're trying to use. So a private investor called Res2Prac wants to put up a nuclear facility in Zambia. So it will be in charge of the technology, it will be in charge of the operations, and they'll just sign a power purchase agreement with Zambia. So Zambia will just be buying electricity from there. So the whole project will just be, the whole power plant will just be owned by the private sector. So through this model, we are guaranteed somebody is going to put up the power plant and is going to spend all the money, and it's just going to be buying electricity under the power purchase agreement. But under this power purchase agreement, it changes maybe after 10 years, they agree on a different tariff. Then we have another one, is called the build, own, transfer. Okay, in this one, a private sector just builds, owns it, let's say 10 years, owns it, then transfers it. It's a very good